We are discussing about the mechanical vibration. Today we are going to discuss about the vibration due to rotating unbalanced mass. Most of the mechanical system driven by electric motors or engine. These rotary elements, rotary systems associate with unbalanced masses. These unbalanced masses, when rotating these unbalanced masses, it produce vibrations. Okay. In this lecture, we are going to discuss how these unbalanced masses, rotating unbalanced masses, producing vibration of the system. Okay, let's continue to the lecture. Okay, today's lecture is about the vibration due to rotating unbalanced mass. This kind of vibration in common in most of the mechanical system, because most of the mechanical system driven by engine or electric motors as the power source, so that every rotating element, rotating systems associate with unbalanced masses. These unbalanced masses produce vibration on the system. Okay, so let me draw this kind of equivalent system for this kind of system. Here we are discussing, we are only consider a 1 degree of freedom system. Okay, let's take the total mass of the system as m. Then let's take stiffness of the system. I would represent by the k. And this is the damper system, overall damper I would represent by this viscous damper c. Then let's take the rotating unbalanced mass in this way. This is the simple m, the rotating unbalance, the simple m unbalanced mass rotating with omega angular velocity. Here we are only consider 1 degree of freedom system. That means it is allowed to move in a vertically upward or downward movement. Okay? That means the vertical movement only allowed due to this force, excitation force. Then this is the system. This is the system we are going to consider. You can see this is the system overall mass. Then this is the unbalanced mass. Then let's take the eccentric distance as simple E. Eccentric distance simple E. The eccentric mass is simple M. Then this due to this rotation of this mass eccentric to this rotating axis, it produces excitation force on capital M. On the capital M. Okay, let's see how to produce excitation force on this vibrating system. Okay, let's take excitation force due to unbalanced mass. Excitation force due to rotating M mass. Then how to obtain this excitation force due to rotating unbalanced mass? Okay, then here this let's take this kind of situation. This is the simple M mass, this is the E. Okay, this is the E. Let's take we are starting the measuring of measurement of T in this kind of horizontal position. T is equal to 0 position. Let's take this is T is equal to T position. Then this is rotating with omega angular velocity. Then this angle is equal to omega t. This angle is equal to omega t. You know, when rotating m mass around this center, centrifugal force is acting in this directions. What is this centrifugal force? That force is equal. This F force is equal m r omega square. That is acting on this m mass it is acting in this direction, on capital M mass it is acting in this direction. Okay, mr omega square, mr omega square. Okay, then here you can see we can resolve this F force acting on this capital M mass in two perpendicular directions, the vertical direction and the horizontal direction. That means we are considering only 1 degree of freedom system. That means we are considering only this vertical vibration only. That means horizontal direction the vibration is restricted. Considering the easiness, we are considering only the vertical direction vibration. We can resolve this force into a two component. That means force acting on this M mass is equal mr omega square. We can resolve into two components. What are these two components? This is equal to f sin omega t, f cos omega t. This is omega t. This angle is omega t. So then we are interested about only this component because we are considering only the vertical vibration. So that this component acting on this m mass we can represent by it's a time varying component. If t is equal mr omega square sin omega t. Okay, sin omega t. You can see this same as in previous lecture. This is the magnitude of the excitation force. This is the magnitude of the excitation force. It is represented by the sin omega t function. That means it is acting like this. T sin function. This is how the excitation force is vary. This is ft. Then this magnitude is equal to f is equal to m r omega square. Keep remember this magnitude of the excitation force also a function of frequency of unbalanced mass rotating. Okay, then this is the excitation force acting on the m mass. Then in a vertical direction, then we can apply Newton's second law considering the motion of m mass. Okay, by applying F is equal ma considering the motion of m mass. Consider the motion of m mass. Okay, same as in previous lecture we discussed in damped force vibration system. So then we can obtain by applying the F is equal to ma. We can obtain this equation. Then what are the F is equal to ma? What are the forces acting on it? Let's take the situation where the system is producing x displacement because of this excitation force, ft excitation force. Let's take this m mass has displaced this excitation force. That means internally generated excitation force I am representing in here like this, internally generated excitation force. Then let's take from this is equilibrium position, it has displaced by a x distance and with the velocity x dot and acceleration x double dot. In this situation t is equal t situation. Okay, so then what are the forces acting on it? Because of the spring compression it is acting let's take we are acting F is equal ma in a downward direction. So what are the spring force? The minus k into x. The viscous damper, viscous friction force, that is equal minus c x dot. Okay, then excitation force plus ft is equal mx double dot so then by taking to one side these terms, we can write mx double dot plus cx dot plus kx is equal ft. What is ft? Sorry, yeah, the r, yeah, that's okay. Instead of the simple r, I'm going to use the e, because it is you may confuse with the ratio r. So I'm going to take the e, m e omega square sine omega t. This is the characteristic equation for this kind of system. You can see that it's a second order non-homogeneous ordinary constant coefficient type differential equation. So then the last class we discussed how to solve this kind of differential equation. Okay, last class we discussed how to solve this kind of differential equation. If we are having this kind of non-homogeneous part as the sine function, we are taken particularly that means the total solution of the differential equation is a xct complementary function solution plus xpt particular integral solution. We are obtaining the complementary function solution by equating this left hand side to 0. That means ee lambda 1t plus be lambda 2t plus for this if you are having this kind of a non-homogeneous part sine or cos function, we are getting m cos omega t plus n sine omega t. Then we can reduce it to a x cos omega t minus 5 in simple trigonometric equations. So then I am going to write this one x cos omega t minus 5, so that is equal to xt. Okay, then in a few minutes after starting the vibration, in a few moment this is damped out, this part is damped out. Okay, after initiating the vibration, in a few moment this is damped out, because when we are discussing about the damp free vibration, we observe this how this is happening. It is damped out in a few period of time, so that we can actually this is remain only in initial moment, but in steady state vibration this part is remaining. So then we are interesting about the system steady state vibration, not the initial vibration. So in steady state vibration, the equation is equal to xt. This is the steady state vibration, x cos omega t minus 5. This is the steady state vibration for this kind of system. Then this is the particular integral solution. The only remaining one is the particular integral solution. That means xp is remaining. So then this is unknown constant. X and 5 are unknown constant. We have to determine this x and 5 by substituting this particular integral solution in the characteristic equation. Okay, characteristic equation. Then in the last class I explained how to obtain this x and 5 by substituting this this kind of differential equation when we are discussing about the force, damp, vibration. Okay, then in this time I am not going to repeat it again, so I will directly give this x and 5 for this kind of system. Then I will directly give that x and 5 values in this situation. Okay, yeah, what is we are getting? Actually we know to substitute that equation by looking at the damp force vibration system, we can obtain that one. Actually, for the damped force vibration system, what we got, the delta st. This is the equation for the damped force vibration system. The 1 minus omega divided by omega n into square, the square of total, the 2 theta omega divided by omega n into square of total, then the square root of total. This is the equation we obtain for the damped force vibrating system. Then the phase shift angle is equal tan inverse 2 theta omega divided by omega n divided by 1 minus omega divided by omega n into square. This is the phi we obtain for the damped force vibrating system. Okay. Then by looking at these two x and phi values, we can obtain the equation for our rotary unbalanced mass system. How to obtain? Then delta st, that is called static deflection. That is equal to F divided by K. We just want to substitute this F and K. F is the magnitude of the excitation force. F is the magnitude of the excitation force. That means considering our system, rotating unbalanced system, what is F? The magnitude of the unbalanced mass. What is the magnitude of the unbalanced mass? This is the magnitude of the unbalanced mass. Okay. M R omega square. Instead of R, I am going to put the E. M E omega square divided by K. Then denominator, the omega divided by omega n into square plus 2 theta omega divided by omega n into square root of total. Okay, this is the x we obtain. The phi is same. The 2 theta omega divided by omega n 1 minus omega divided by omega n into square. The phi is same. So then the further this equation we can rearrange. How to rearrange this equation? I am going to introduce omega n square. Omega n square is equal k divided by n. So instead of k, I am going to put the k is equal capital M omega n square. Instead of k, I am going to put capital M omega n square in this equation. Okay, then equation, let's see what happens to this equation. M divided by capital M instead of k omega. Yes, the E omega divided by omega n into square divided by 1 minus omega divided by omega n into square of total plus 2 theta omega divided by omega n into square root of total. Okay, this is the equation finally we obtain. Then this equation again I am going to rearrange to this kind of format. That means this is called I'm going to divide the x by this term. That is equal to ME divided by capital M is equal to then omega divided by omega n into square divided by 1 minus omega divided by omega n into square of total plus 2 theta omega divided by omega n into square root of total. This is the equation finally we obtain. Then this is called normalized magnitude. That is normalized magnitude. That means it actually a measure of magnitude of vibration, amplitude. That means amplitude of vibration it represents. Then this is this normalized magnitude is a function of frequency ratio. But in this situation, slightly different with the forced damped vibration system. In a forced damped vibration system, for the numerator we didn't have the frequency ratio, but in this situation, for the numerator also we are having frequency ratio term. Okay, then let's see how to vary this normalized magnitude with the frequency ratio. Okay, with the frequency ratio. Okay, then I'm going to draw this graph. This graph is representing this is the omega divided by omega and the frequency ratio R. Then this is that is equal to mx divided by E into simple n. The variation of normalized magnitude with the frequency ratio we are going to discuss. Then what is the equation now? So I will write that equation in here also. X divided by x m divided by em is equal to omega divided by omega n 1 minus omega divided by omega n into square plus 2 theta omega divided by omega n into square, then the square root of total. Then this is the equation. Then you can see this normalized magnitude is a function of frequency ratio. Then let's see how this is vary with the how this normalized magnitude is vary with the frequency ratio. So let's consider theta is equal 0 situation. This term is equal to 0. Then what happen? Let's take the situation where the frequency ratio is equal to 1, R is equal to 1. That means omega is equal to omega n situation. That means rotary angular velocity is equal to the system natural frequency omega n. Then in this situation what happen? You can see we have taken the square here. Then what happen? A frequency ratio is equal to 0. Denominator is equal to 1. Numerator is equal to 0. That means we have to start with the 0 essentially. If frequency ratio is equal to 0, then every moment the normalized magnitude is equal to 0. So essentially we have to start from the 0. Then what happens when increasing gradually the omega divided by omega n from the 0, what happens when it reaches to the 1? What happens to the denominator? It reaches to the 0 because 1 minus omega divided by n. Then when it reaches to the 1, when this term reaches to the 1, what happens? This entire denominator reaches to the 0. What it means, when frequency ratio reaches to the 1, this entire expression goes to the infinity. That means it having this function having the vertical asymptote at r is equal 1. That is, we can represent like this. Just take this is the r is equal 1 position. It having the vertical asymptote. Vertical asymptote that we can draw like this at theta is equal 0 situation. This is the vertical asymptote. Okay, vertical asymptote. Then what happened when the omega divided by omega n increases from 1, increases from 1, then it also start from the, when it just beyond the 1, it also starting from the infinity. It also is starting from the infinity. Then what happen when it increases? What happen? For higher values of omega divided by omega n, for higher values of omega divided by omega n, what happen? We can neglect 1 in here because this is very high compared to the 1. So that in a denominator we are remaining omega divided by omega n term. Okay, because we are taken the square. Then sorry, this one should be a square. Sorry, this one should be a square. Yeah. Then what happen when taking the, for higher values of omega divided by omega n, for higher values of rotating frequencies, what happen? This part is dominant compared to the 1. So we can neglect the 1 in here. So then as the denominator we are having omega divided by omega n term in this way. So in a numerator we are having omega divided by omega n in a square. So the finally we are reaching to the 1, when increasing omega. For higher values of omega we are reaching to 1. So that means we are starting with the infinity, then we are reaching to the 1. So what how to draw that one? That means it having the horizontal asymptote. It having this is equal to 1. It having the horizontal asymptote like this. It having horizontal asymptote like this. Okay, horizontal asymptote like this. Okay, then this is for the theta is equal to 0 situation. Theta is equal to 0 situation. Theta is equal to 0 situation. This is theta is equal to 0 situation. Then let's see another situation. The theta is equal to none. Theta is not equal to 0. Let's take the as initial. Let's take theta is greater than 1 situation. Theta is greater than 1 situation. That means for higher values of theta is greater than 1 situation, what happen? Again it has to start from the 0 because in each situation the omega divided by omega n is equal to 0. This term, entire term is equal to 0. So we have to start from the 0. Then what happen? If theta is greater than 1 situation, it never goes beyond the 1. This term never goes to beyond the 1. Why is that? If this term is greater than 1, for any value of frequency ratio, if this term is greater than 1, it never goes to beyond the 1 because the denominator is greater than numerator. If remember, if theta is greater than 1 situation, only theta is greater than 1 situation, always denominator is greater than numerator. So that this ratio is less than 1. Okay, because you can see for higher values of theta, you can see this term is greater than this value always. So that again what happen? It never goes to never reaches to 1, then again what happen? When increasing the frequency ratio, what happen? Entire ratio goes to 1. Okay, sorry, in here it is this keep remember this one, there should be a bracket square. So then we can draw that curve like this, okay. If any theta is greater than 1 situation, theta is greater than 1 curve, that means let's take this is theta is equal to 1, then any theta is greater than 1 value, we are represent by like this, theta is equal to 2, like something like that. Okay, there should be a square in here. Okay, then what happen, any theta is less than 1 situation, it can goes to beyond the 1, it can goes to beyond the 1, because in that situation numerator can greater than the denominator, so that it can goes to the beyond the 1, so that for that kind of graph we are having this kind of value, this kind of shapes. This is equal to 0.05, let's take this is equal to 0.25, then this take this is equal to 0.5, something like this. You can see the maximum amplitude in this situation, you can see it is very according to this curve, okay. The maximum normalized magnitude is vary in non theta is non-zero situation, like this, is very like this, okay, is very like this. This is how we are obtaining this graph, how the normalized magnitude is vary with the frequency ratio by looking at this equation, okay. Then let's see how phase angle is vary with the frequency ratio, how the phase angle is vary with the frequency ratio. That frequency ratio is equal to, that means the 5 is equal, sorry, phase shift angle is equal to tan inverse 2 theta omega divided by omega n divided by 1 minus omega divided by omega n into square, okay. Then let me you can remember, I think, in the tan graph how it is behave. Tan graph, let's take the tan graph, tan function graph, let's take this is 0 angle, so then at the 5/2 with having the vertical asymptote, at the 5/2 with having the vertical asymptote, again at the, yeah, here it is 5/2 minus 5/2, then this is 0, then let's take this is 5, okay. Then what is the shape of this curve? Something like this, and it is again it is starting from the vertical asymptote, yeah, it is starting from here, okay. This is how the tan function, tan graph, yeah, according to, by looking at this tan graph, we are going to draw how the 5 is vary with the frequency ratio, Okay, we are interested about how 5 is vary with the frequency ratio. Okay, let's take this is the frequency ratio omega divided by omega n. This is how the 5 is vary. Let's take this is 5, and let's take this is 90 degree, and let's take this is 180 degree. Okay, so then what happened, let's take the frequency ratio is equal to 1 situation also, r is equal 1, r is equal 1, that means omega is equal to omega in situation. Then let's take this is the equation. See the equation. By looking at this equation, we are going to draw this how this 5 is vary with the frequency ratio. How 5 is vary with the frequency ratio. Then what happens? Let's take the condition. The theta is very small. Let's take the theta is very small. The very small. In that situation, what happens? This part is very small. This part is very small, closer to 0. Closer to 0. Tan inverse 0. Tan inverse 0 means that is closer to this value. So then what happens when increasing the frequency ratio? This part goes to denominator goes to 0. Then what happens to this term? The entire term increases. Entire term increases to infinity. Tan inverse infinity means that value goes to the 90. So that how it happens. We can represent like this in this way. For a smaller value of theta, something like this. Okay, rapidly goes to. So then after this it is starting with the, then after it beyond the frequency ratio is starting with the negative infinity. Then again we are starting with the negative infinity. I mean, for example, I will draw this some values for the tan. Let's take this is 0.5 minus this is 1. Then in this direction the infinity. Okay, some values you can understand easily. 0.5 positive value, minus 1. Then this is the positive infinity. Then this is negative infinity. If it is starting with the negative value, you can see, then this negative value is reduces gradually, because when increasing, when this frequency ratio moving away from the 1, the negative value reduces, so that you can see it reaches to the 5. That means we are having this kind of graph. Okay, that means this value is equal to theta is equal to something like 0.001, like. Okay, then this graph is representing theta is equal 0 situation. Theta is equal 0 situation. Okay, then this is theta is equal very small situation. Then what happens if theta is very high situation? If theta is very high situation, let's take this value is very high. This part is dominant. This theta is dominant. So then in that situation, this is how it is vary. When frequency ratio reaches to 1, it having a sudden increase of this entire ratio, then it suddenly reaches to a 1, something like this. Okay, something like this. So then beyond the 1, what happen? It reaches to the 180, that means the 5, but in slowly, like this, something like this. So then this is like theta is equal to 5, something like this. Okay, the in between these values we can represent like this. Theta is equal 0.05, then the theta is equal 5 situation, 0.5 situation, theta is equal 0.5 situation, something like this. This is how the phase angle, variation we are obtaining by looking at this equation and tan function. I think you all more clear with this vibration, how rotating unbalanced mass produce vibration on a mechanical system. I think you all more clear with this theory. Then let's move to some example problems related to this kind of problem situation. Then this is the one we are going to consider first. Okay, this is the one we are going to consider. Just read the problem. Consider a machine with a rotating unbalanced mass as shown in figure. At resonance mean omega is equal omega in situation. At resonance, the omega is equal omega in situation. Omega is equal omega in situation. The maximum amplitude of a vibration measured to be 0.1. That means the maximum amplitude of the vibration mean x. In a steady state vibration we are discussing x is equal to 0.1 meters. From a free decay of a system vibration, that means you know how to measure the theta, overall theta for a system by measuring the amplitude. The free decay of a system vibration, the damping ratio is estimated to be theta is equal 0.05. From manufacturing, that out of a balance of mass m0 is estimated to be 10%. 10%. That means if this is m, that is equal to m divided by simple m into 100 is equal to 10%. Okay, 10%. The 10%. Estimate the E. That means this eccentric radius we have to estimate, and hence the approximate location of the unbalanced mass. Also determine how much mass should be added to the system to reduce the amplitude of the vibration to a, that means how much mass added to delta m to reduce amplitude of vibration to a 0.01 meters. Then let's see how to do this problem. Okay, in this system we have to determine this eccentric distance first. That means this E value we have to determine. This is the system we are having. So then this is amplitude of vibration. In steady state situation, this amplitude of vibration is given. This amplitude of vibration is equal to 0.1 meters. Okay, 0.1 meters. So then we know the equation of x equation. We know what is the x equation. X is equal me, capital M, divided by omega n into square divided by 1 minus omega divided by omega n into square plus 2 theta omega divided by omega n square of total, then the square root. Okay, this is the equation for x. Okay, amplitude of the vibration in steady state situation. In this equation, the problem says it happened the resonance. The omega is equal omega in situation, it happened. That means this ratio is equal to 1. This ratio equal to 1, that means this equation is reduced to x is equal me divided by capital M, then divided by this ratio is equal to 1, means this term, entire term is equal to 0. In here it is remaining only 4 theta 4 theta square, then the square of total, then finally we are remaining as x is equal me divided by capital M divided by the 2 theta. Okay, then x is equal me capital M 2 theta. Okay, we are remaining. Then what is the x is measured? X as measured is equal to 0.1. So m divided by m is obtained from the data sheet, that is equal to 10%. 10% mean 0.1. It is also 0.1. Then the eccentric mass E. Then we are having for theta, that is given, no, 0.05. 0.05. 0.05. Then for the E we are having 0.1 meters. 0.1 meters. 0.1 meters. That is when eccentric distance is equal to 10 centimeters. Eccentric distance of this m mass is equal to 0.1 meters. Okay? 0.1 meters. Then as the second part, it says also determine how much mass should be added to the suggested system to reduce the amplitude of vibration to a 0.01 meters. Now at resonance, this also happened in resonance. Resonance means in this equation we can use, this equation we can use. So finally we want 0.01 amplitude. Then how much mass we have to add? How much mass we have to add? In this situation, let's see this ratio. In this situation, let's take this is m divided by capital M. Then again eccentric distance is not changing, 0.1 divided by 2 theta, 2 into 0.05. Then we can cut these values. So then the final we are remaining m divided by capital M should equal to 0.01. 0.01. What it means, the m divided by capital M should equal to 0.01. In the previously what happened, m divided by capital M is equal to 0.1. Okay, m divided by capital M equal to 0.1. This is the existing system, but we have to get m divided by m to a 0.01 situation. 0.1 situation. Okay. Then what happened? How much of mass we have to add? How much of mass we have to add? That means to convert this ratio, to a, it is better to write in this kind of way. The 10, you may understand the m. Capital M divided by m is equal to 100. Okay, this is m is not changing. Then m in this situation, m, just take in this situation m1, this is m2. Okay, the how much mass we have to add to get the this value? In this situation it is 10 times, but should be 100 times. So it should be this ratio should be 100 times. What kind of mass we have to add? In this situation, the 10 m is equal m2. 100 m is equal m1. Okay, then we are having 10 m mass for m2. Then how much we have to add? That is equal to 90 m mass we have to add to the m2 mass. Okay, 90 m mass we have to add to the m2 mass. Then finally we are having 100 mass, 100 m mass. So that means delta m is equal to 90 m, 90 m. Okay, 90 m mass. That means as a ratio we can give it as the consider the m mass that is equal to delta m. The delta m mass is equal to, considering this overall mass, that is equal to, as the delta m mass, that is equal to 9 times m mass. Okay, 9 times m mass is the answer. I think you all more clear with this today's lecture. Okay, this is all about the vibration due to rotating unbalanced mass. Okay, let's continue on next day class. Thank you.